Hello there, pre-calculus students. This is Mr. Kashi again. This video we're going to go over our second day on probability. We're going to be going through independent events and dependent events, and then we'll have a second video on conditional probability. So we just want to get some definitions down here first. So independent events is where the occurrence of one event has no effect on the occurrence of another event. And this would be, we'll be going through some examples here on the next slide. And the opposite of an independent event would be a dependent event, and that's where the occurrence of one event affects the occurrence of the other event. So one, it doesn't matter. Two, the second one does. So independent, one event doesn't affect the other one. Dependent, the event does affect the other one. So independent event examples, this would be flipping a coin. This whatever you get the first time, heads or tails, has nothing to do, it does not affect what you would get the second time. Another example would be rolling dice. If you get a 3, if you roll 2 dice and they add up to get a 3, you are not more or less likely to get a 3 the next time you roll. It's the exact same probability no matter what you get the first time. So this would be, another one would be drawing a card from a deck. And we're going to talk about this a little bit more, but then it's going to be then replacing it. And that's what makes it an independent event. If you don't replace it, it's no longer independent. It becomes a dependent event. Another independent event would be spinning a spinner. And these, whatever you spin the first time, it has nothing to do with what the outcome will be after you spin it a second time. They do not affect each other at all. So we do want to go through some examples of the independent events. So we're going to talk about actually calculating these probabilities. So consider rolling 2 six-sided dice twice. What is the probability that the first roll is a doubles and the second roll is a 10? This would be a good reminder to have your cheat sheet out, because if you have doubles, that should be 6 out of 36. And when we're doing independent events, we're just using the multiplication principle. So we have 3 times 36, because there's 3 ways of getting 10. And you could put that into your calculator, and you will find out that it is 0.0139, which is under 1.5%, which is not very likely. All right, moving on to B. What is the probability that the first roll is an 8 and the second roll is doubles? Well, there's 5 ways to get an 8, so that's 5 out of 36. And then the second roll would be a doubles, which there's 6 ways of getting doubles. Doubles would be 1 and 1, 2 and 2, 3 and 3, 4 and 4. You multiply that out. We did not increase our our probability very much. 0.0231, which is obviously just over 2%, not very likely at all. Then finally, C, what is the probability that the first roll is an even sum and the second roll is greater than 8? Well, if you take a look at your chart and you count up the evens, you should find that there are 18. And then how many of them are greater than 8? Well, there are 10 that are greater than 8. So now our probability is getting a little bit higher. We have 0.1389, or just under 14%, if we were to find out what that percent is. Okay, so those are independent examples. Pretty straightforward. You're just finding the probability of the first event, probability of the second event. You're multiplying them together. And neither of these events affect each other. But moving on to our dependent. this would be something that's a little bit more, you have to pay attention, make sure that you are keeping track. Okay, so a gumball machine contains 100 gumballs, and there's 20 red, 20 blue, 20 green, 20 yellow, and 20 white. Find the probability of each event. And I will say, after each calculation that we do here, we are going to be starting from the 100 again. So after we complete the problem for A, we're going to start back at 100 for the problem at B. We're not going to keep going. So this is the probability of blue and then white. Well, there are 20 blue, and there are 100 total. And then we're going to multiply that by white, which there are 20 white available, but there aren't 100 available anymore because we already took one blue out. So actually this second one goes down to 99. Okay, and if we were to multiply that out, we would get 0.0404. And if you were to want to do this using combinatorics, you would say that on the top that would be 20 squared over, this would be 100 permutation 2, because order does matter in this case. I just want to make sure that these dependent event examples, we know that that this is no replacement. That's what makes it a dependent event. If we were to put the blue, if we were to, in this first example, if we were to choose the blue gumball and then put it back, we'd still have 100 to choose from. But that's why we made it a gumball machine, because the likelihood of you actually putting the gumball back after you get it out, don't even know how you would be able to do that. So that's why the context of the problem kind of tells us that it's going to be dependent. This next, we're going to start back at 100 for this problem. So we're choosing green, which we got 20 out of 100. Then red, which we have 20, but now we're down to 99 gumballs because we took the green one out. And then blue, we're at 20, and now we're down to 98. And if you were to multiply that out, you would get 0.0082. Not very likely that you'd get those exact green, then red, then blue. Once again, in combinatorics, it would be 20 to the third, and then we would have 100 permutation 3. Okay, two more here. Here we have, we're doing 3 blues in a row. The likelihood of that happening. Hopefully you can kind of just understand the context that that's not very likely to happen. But to calculate it, we have 20 out of 100. And then we are going to be going down because we're one less blue to choose from, and now we have one less total to choose from. So now it's not 20 over 99, now it's 19 over 99. And then we choose another blue, and that would be 18 over 98. So both the top and the bottom have to decrease by 1 because we're choosing the same color over and over again. So here, this would multiply out to 0.0071. So less than 1% of being able to choose 3 blue, randomly get 3 blue in a row. Then last, we have choosing 2 yellow. Basically just the first 2 steps of the one above. We have 20 out of 100, and then 19 out of 99. Getting 2 yellow in a row, or basically 2 of any color in a row, would be almost 4%. So a little bit more likely than getting 3 in a row, obviously. But that is 4 examples of dependent events, and I would say the more challenging part is finding out whether they are independent or dependent, finding out if one affects the other before you even start the math and using the combinatorics for the examples.